Over the last few lectures, we have been describing the path integral formulation based calculation of the propagator for a simple harmonic oscillator. In the first lecture on this topic, we have looked at how we can simplify the calculation by looking at fluctuations about the classical path. We have then gone on to talk about a particular application of the propagator, which is figuring out the energy eigenfunctions and eigenvalues from the propagator that we have calculated. Today's lecture will involve an alternate scheme for calculating the propagator for the simple harmonic oscillator. We have already found out the result using one method, but it is actually quite useful to know several different methods for calculating the same simple thing, because each of these methods can be generalized for other more complicated situations later. This one involves using Fourier components for our fluctuating paths. Let me remind you that what we did in the last lecture was, for each path, we considered it to be a fluctuation about the classical path. So x of t was x classical of t plus capital X of t. And we figured out that because the Hamiltonian was quadratic and the action was stationary for variations around s classical, Sx essentially ends up becoming s classical plus m by 2 integral from ta to tb of x dot square minus omega square x square, integrated of course with respect to t. And the important thing which made our life very easy as far as evaluation of this path integral part for the p-factor was concerned is that capital X vanished both at ta and at tb. And that actually helped us to easily calculate the p-factor, the normalizing factor, f of tb comma ta. Now we are going to show you another way of calculating f of tb comma ta here. Rather than writing down the entire Gaussian integral and then evaluating it by diagonalizing the coefficient matrix. Of course, the reason why even after you could write it out this way, the evaluation was still not entirely straightforward, was that you had to find out the determinant of a rather large matrix for this, and the determinant was not very easy to calculate. Easy, of course, is relative. There are other path integral calculations which are way more complicated than this one, but this was reasonably simple but still not too simple. Let us put it that way. And why did you have to calculate the determinant of this large matrix? Basically, the quadratic term that you had in the exponent in the Gaussian integral, that term did not give you n independent integrals. They gave you an n-dimensional integral where the terms were coupled with each other. And essentially what you would want to do is decouple them using what are called normal modes. And for the decoupled quadratics in the exponent, the integral would become easy. We have described all this earlier in the series. But ultimately what happens is, you end up with a result which depends on the eigenvalues of that matrix, or rather the product of its eigenvalues, and that's where the determinant comes in. All this could have been avoided and the calculation would have been much simpler if the individual quadratic pieces had been decoupled from each other, which is not the case because of the presence of the xj plus 1 minus xj whole square term, which gives you the twice xj plus 1 xj in the exponent. It turns out that there is a pretty straightforward way of decoupling the quadratic terms here, and that is by introducing a Fourier decomposition of the paths. Note that all our x of t's are defined only in the interval between ta to tb, and it vanishes at both ends, which means that we can use our elementary mathematical physics result that any such function can be written down in a half-period expansion using sine waves. So capital X of t can be written down as a sum over infinite number of Fourier modes of bk sine k pi t minus ta over capital T. Capital T, of course, is tb minus ta. And this immediately tells us that x dot is what you get by differentiating this term by term. So instead of bk here, you are going to get pi k bk by t, and the sine, of course, becomes a cosine. Now note that for this expression for capital X of t and x dot of t, you can easily calculate the action in terms of the bk's. For example, if you integrate x square dt from ta to tb, you are going to get bk times bk prime. Remember, you are multiplying two infinite series together. The indices are both dummy and they have to be changed so that there is no confusion between the two dummy indices. So you have bk prime summed up over k and k prime both from 1 to infinity. Of course, bk prime is not the integral or not the summand. There is an integral which you have to do after that. And this is something which you all must have done in your early mathematical physics classes. If you haven't, you can of course use elementary trigonometry to calculate this integral. And this integral turns out to be capital T by 2 times delta kk prime. So this particular integral, the first term that you have becomes t by 2 sum up from k equal to 1 to infinity of bk square. The x dot square integral proceeds in along the same fashion. Instead of sine, you have an integral involving products of cosines, but the result is very much the same. And you get something which looks very similar. You get capital T by 2 times sum from k going from 1 to infinity of pi square k square bk square by t square. This summand is a bit more complicated simply because instead of bk, you have pi k bk by t in x dot. Now, if you calculate the action, or rather, the change in the action from the classical value, which is of course this integral m by 2 integral from ta to tb of x dot square minus omega square x square with respect to time, you end up with mt by 4 times an infinite sum. So action is still an infinite sum, but now notice that this sum has no cross terms between different values of k. Each k appears only once. Now the all-important point is the following. You can think of your initial variables x1, x2, xn as being replaced by a new bunch of variables b1, b2, bn. So this is basically a change of variables, and since you are taking the limit as n goes to infinity, you had infinitely many different x's to begin with. Now you have infinitely many different b's which you are integrating over. Of course, when you do this change of variables, you have to bring in an overall factor which connects the two measures. That is, you have to bring in the Jacobian for the transformation. Now that Jacobian can be a pretty complicated expression, but it's something which does not depend on b1, b2, bn. So it's a constant. So right now, the integral that we wanted to do, the discretized integral to calculate f of tb comma ta, that can be replaced by an integral over the b's. But we will not get a complete expression out of this, basically because we will have an overall multiplying constant. But having said that, if you leave that constant issue out for the time being, the exponent is a sum for individual bk square times some factor, which of course becomes product of the individual exponents. And instead of integrating over db1, db2, dbn, you could just simply integrate over the db's first and then multiply the results. So instead of having to deal with a huge n-dimensional integral, what you are really going to do is n independent one-dimensional integrals which are trivial to work out. And if you use the standard result, what you will get is 1 by square root of pi square k square by t square minus omega square times some several other factors. Now all these factors can be plugged together and you can push them into the constant. That's why I have deliberately written the constant now as constant with a prime. That indicates that this constant is not the same as the previous constant. Followed by an infinite product of 1 over square root of 1 minus omega square t square by pi square k square. Now the reason why I have decided to write down the product in this particular fashion and absorb the rest of the factors in the constant is the following. This particular infinite product has a very, very simple formal expression. by using something called Euler's product expansion for sine z by z, can write down that product as square root of omega t by sine omega t. I will discuss Euler's formula in a bit more detail soon, but for the time being, this is basically what the central result is. Our normalizing factor works out with some constant multiplied by square root of omega t by sine omega t. But notice that the constant here has a huge bunch of extra factors which came in from the Gaussian integrals, which I did not really retain because I wanted to maintain the form for Euler's formula. It also had a huge prefactor which came from the infinite dimensional Jacobian. So it seems to be a rather tall order to try to calculate that constant, but without that constant, the normalization factor f will not be completely known. There is a way out, however, and the way out is pretty straightforward. We know that when omega is taken to 0, our physical system, the simple harmonic oscillator, goes over to a free particle. And we do know that for a free particle, the normalization factor has to be square root of m divided by 2 pi h cross I capital T. And this immediately tells us from the limit that the constant prime, the new constant, has to be square root of m by 2 pi h cross I capital T. Throwing this one in, we see that the normalizing factor for the harmonic oscillator f of tb, ta turns out to be our by now familiar result, square root of m omega by 2 pi h cross I sine omega t. So we have de-derived the propagator for the simple harmonic oscillator using this Fourier decomposition approach. Now, you might say that this is just one more different way of working out the same result. So what's the big deal here? The answer is that there are other situations also where this particular decomposition will be useful. And moreover, if you remember, we had a bit of a problem with our result for the propagator. It worked only as long as omega t was less than pi. That is, only as long as tb minus ta was smaller than half a time period for the harmonic oscillator. Now what happens when you go beyond that? We will see in a while that the Fourier decomposition method will give us a way out and suggest exactly how to correct our propagator when we go to larger and larger times. But before we go there, let us take a look at this Euler's formula which we used here and try to understand where this came from. What I am going to tell you is not really a proper mathematical derivation of Euler's formula. That requires something rather advanced called the Weierstrass approximation theorem. But the rough and ready argument that I am going to give you is essentially what Euler himself used to derive his result. And what Weierstrass theorem actually does is that it sort of says that the non-rigorous arguments we are applying here can actually be made quite rigorous. So, in order to understand the Euler formula, let us start from a familiar result, that if you have a polynomial f of z which has zeros at z equal to a, b and c, then f of z can be written down as a product of z minus a, z minus b, z minus c and so on with an overall factor capital K. And you can easily rewrite this by absorbing some of these minus a, minus b, minus c factors inside capital K in the following form. F of z will be some constant k prime into 1 minus z by a times 1 minus z by b times 1 minus z by c and so on. Now all this is fine as long as you are dealing with a finite order polynomial. What Euler did was to use the same result for the function sine z by z, which of course is not a polynomial but an infinite series. It does have zeros, but rather than a finite number of zeros, it has an infinite number of them. The zeros are at plus minus pi, plus minus 2 pi, plus minus 3 pi, plus minus 4 pi and so on. So Euler pretended that you could actually use the polynomial result here as well. You could write sine z by z as 1 minus z by pi times 1 minus z by minus pi times 1 minus z by 2 pi times 1 by z by minus 2 pi and so on with an overall factor. And that overall factor, he argued, had to be 1 because when z goes to 0, sine z by z goes to 1 in the limit, and all these brackets, of course, go to 1 in their individual limits. So the constant k prime has to be 1. And this gives rise to Euler's result that you can write sine z by z as an infinite product, and he preferred to couple the 1 minus z by pi, 1 plus z by pi and similar terms together and wrote them as 1 minus z square by pi square times 1 minus z square by 4 pi square times 1 minus z square by 9 pi square and so on. So this was the infinite product where you were multiplying 1 minus z square by pi square k square for all k running from 1 to infinity. And this Euler claimed was sine z by z. As I have said, this argument may be a bit non-rigorous. In fact, Euler gave a different derivation of this later, which was a lot more rigorous than this one. But if you use Weierstrass's method, you can actually make these arguments perfectly rigorous. For the time being, this is all I am going to say about the derivation of the Euler formula. But before we sign out of this topic altogether, let me bring to your attention a rather important fact from mathematical physics, which is not really relevant to path integrals as such, but there's such a nice result that I cannot resist sharing it with you. So, as Sheldon in the Young Sheldon series or the Big Bang Theory series is bound to say, fun fact, you can actually calculate the value of zeta 2, the Riemann zeta function for argument 2 using this particular identity. Zeta 2, if you remember, is nothing but 1 by 1 square plus 1 by 2 square plus 1 by 3 square plus 1 by 4 square and so on. To see how that follows from Euler's identity, you just write down sine z by z using Euler's identity, the infinite product on the left here, and its series expansion, which you get simply by dividing the series expansion for sine z by z on the right. Now, if you want to look at the coefficient of z square, the right hand side clearly tells you that that is minus 1 by 3 factorial, minus 1/6. What about the left hand side? On the left hand side, you have an infinite product of 1 minus z square by pi square k square. So in order to get an overall factor with z square only, what you have to do is take 1 from each and every one of the brackets except from one of the brackets where you're going to take the z square term. And that, when you add all of them together, will give you minus 1 by pi square, minus 1 by 2 square pi square, minus 1 by 3 square pi square, and so on. And this, of course, is nothing but minus 1 by pi square times zeta 2. And this, as we have already figured out, actually has to be minus 1 by 6. And this tells you that zeta 2 has to be pi square by 6, which is a pretty familiar result, which I'm sure most of you already know. I'm sure that all of you know other ways of deriving this result, but this one is pretty interesting. In fact, you don't have to stop at zeta 2. You can actually calculate zeta for all even integers, zeta 2n, using this particular identity. In fact, it is a pretty interesting exercise to try to calculate at least zeta 4 from this identity. Why don't you just try it yourself? It's actually pretty interesting. Let us return once again to the propagator. And as promised, I'm going to now discuss what happens when your time interval becomes large enough that you cross half a period. This is the topic called the Maslov correction, because of course Maslov is the one who introduced this correction for the first time. So just to remind you, our expression for the simple harmonic oscillator propagator is valid as long as omega t is less than pi. But if you now go back and look at the product of eigenvalues which went into the calculation for the normalizing factor, you would realize that when omega t exceeds pi but is less than 2 pi, then the product that we had to deal with, this 1 minus omega square t square pi square times 1 minus omega square t square by 4 pi square, etc. This actually has a negative factor. The very first factor here is negative. All the other factors are still positive because omega square t square is actually less than 4 pi square and therefore less than 9 pi square and so on. All the second, third and subsequent factors are positive. The first factor happens to be negative. Which means that in the square root of the product that we are going to get, this will contribute an extra factor of 1 by square root of minus 1. That is, you are going to get a minus I, which of course is e to the minus I pi by 2. Now, every time you cross a multiple of pi, that is when omega t becomes bigger than 2 pi for example, then the first two factors here will actually become negative and they will contribute 2 factors of minus I in the square root. In general, when omega t is between n pi and n plus 1 pi, what we will get is n powers of minus I, that is e to the minus I n pi by 2. This is what is called the Maslov factor. So, taking the Maslov factor into account, our propagator will essentially have this form. Root over m omega by 2 pi h cross, the sine omega t has now become mod sine omega t. Remember, every time you take out a minus sign from the square root, you are left with a product of only positive numbers, which means the product is no longer sine omega t, it's mod of sine omega t. The I has come out from the square root and has become e to the minus I pi by 4. That was the I that was already there in the normalizing factor. In addition to that, you have e to the minus I capital N pi by 2, where capital N of course is determined by how many half periods have omega t crossed. The rest is of course the classical action for the classical path and so on. But this particular factor turns out to be pretty interesting. And what happens when omega t is exactly equal to pi is also very, very interesting. After all, this particular expression as it stands would diverge when omega t approaches pi. But a more careful consideration will show that this will then give you a delta function. I'm pretty sure the more mathematically minded among the viewers would have spotted that the argument that I've given you for the Maslov factor is really not very rigorous. After all, you are definitely going to get 1 by square root of minus 1 factors for each of the crossings of this multiples of pi for omega t. But which square root of minus 1 are you going to get? Are you going to get I or minus I? That's not really very obvious. Also, I've claimed that you're going to get minus I from each of the crossings, but it could very well have happened that you get minus I from one crossing and plus I from another. So in order to completely justify the Maslov factor, we would have to look at this more rigorously. One way in which we can make this calculation for the Maslov factor more rigorous is to fall back upon the spectral representation for the propagator that we have studied in the last lecture. Indeed, the mathematical detour that we had executed in the last lecture, where we talked about the Mehler's formula, will also come in quite handy in this rigorous derivation. So let us now see how that comes about. Let me just remind you that the spectral representation for the propagator in general goes as follows. You have to sum up over all energy eigenfunctions labeled with n, the index, running from 0 to infinity, the following quantity: e to the power minus I en capital T by h cross times psi n xb times psi n star xa, where capital T is the time interval tb minus ta. Now, in the special case of the harmonic oscillator, we know that En, the nth energy level, is given by n plus half h cross omega, and psi n, the nth wave function, is 1 by root over 2 to the n factorial times 4th root of m omega by pi h cross e to the power minus zeta square by 2 times hn zeta, where hn stands for the nth Hermite polynomial and zeta is the dimensionless parameter which is related to x by square root of m omega by h cross times x. Now remember, this is exactly what we had derived in the last lecture, starting from the propagator. But for this, we had used the value of the propagator that we had derived already using the previous arguments, and there we had to confine our time interval to within pi by omega. However, once we have got the wave function and the energies either from the propagator itself by the argument that we had executed in the last lecture, or simply by the fact that we know these values from previous exposure to quantum mechanics. Elementary quantum mechanics courses, of course, teach the harmonic oscillator in some great detail. We can now use these results to see what would happen to the propagator where capital T were arbitrarily big, not necessarily confined to the range between 0 to pi by omega. Now, if we substitute these results for En and psi n, the propagator takes the following form. You get a square root of m omega by pi h cross from the two psi's inside. Then you have a sum n going from 0 to infinity, e to the power minus I n plus half omega t. That's of course En t by h cross times e to the minus zeta a square plus zeta b square by 2 to the n factorial. Once again, two square roots of 2 to the n factorial coming together here, times hn zeta a times hn zeta b. Zeta a and zeta b are of course the dimensionless parameters corresponding to xa and xb. Now we had already seen that our expression for the propagator breaks down rather badly when omega t is an integer multiple of pi. For the time being, let us not talk about that case. Let us talk about the situation where omega capital T is not an integer multiple of pi. So, by calling omega t by pi's integer part capital N, we can write omega t as capital N times pi plus omega tau, where omega tau is the number which is between 0 and pi. And once you substitute that, this e to the minus n plus half omega t factor breaks up into several pieces. You of course have an e to the minus n plus I n plus half capital N pi, and you also have an e to the minus I n plus half omega tau. Now what I will do is I will separate out this into several factors, each of which will become useful in what is going to come. The very first factor that I have written down is e to the minus I by 2 capital N pi. This should be familiar to you as the Maslov factor. And ultimately we will want to show that this is the factor which sits in the front of the propagator when omega t exceeds pi. The next term that you have is minus 1 to the power small n times capital N. You have an e to the minus I omega tau by 2. And finally, you have this e to the minus I omega tau to the power n. This complex number to the power n is actually going to turn out to be very important. I've already mentioned Mehler's formula to you, and if you remember Mehler's formula, you would realize why having something like z to the n is going to be very useful, especially because you have a sum over n going from 0 to infinity, and you have products of two Hermite polynomials. Plugging this in and taking the terms which do not depend on small n outside the sum, we end up with the following form for the propagator. You have square root of m omega by pi h cross, of course. Then you have e to the minus I by 2 n pi, capital N pi, which is the Maslov factor, or which is going to be the Maslov factor when we complete our calculation. Then you have e to the minus I omega tau by 2, e to the power minus zeta a square plus zeta b square by 2. The sum that is left here is a sum from n going from 0 to infinity of e to the minus I omega tau to the power n by 2 to the n factorial minus 1 to the power capital N times small n, followed by the product of two Hermite polynomials, nth order Hermite polynomials at zeta A and zeta B respectively. Now this looks almost exactly like what Mehler's formula would have, but you have an extra minus 1 to the power capital N times small n here. But that is actually rather easy to handle. If you just remember the parity property of the wave functions of the harmonic oscillator, which also is shared, of course, not only by the wave function but also by the Hermite polynomials themselves, that if you change the sign of psi n's argument, psi n minus zeta is going to be minus 1 to the n times psi n zeta. So this thing actually can be rewritten in the following form. You can get rid of this and change the argument here. In fact, change any one of the two arguments. I'm just preferring to do it to zeta b minus 1 to the capital N times zeta b. Of course, if capital N is even, minus 1 to the capital N is 1 anyway and no change occurs here. If capital N is odd, minus 1 to the capital N is minus 1. And then you are really using this form. Now, this looks exactly like the Mehler function. Let me remind you that the Mehler function was this generating function for the products of two Hermite polynomials, sum over n going from 0 to infinity of hn zeta a times hn zeta b by 2 to the n factorial times z to the n. This turned out to be equal to exponential of twice zeta a zeta b z minus zeta a square plus zeta b square z square by 1 minus z square whole divided by square root of 1 minus z square. We have seen how this formula is derived and used in the last lecture. But I would like to point out something which we did not worry about too much in the last lecture. This generating function, seen as a function of the complex number z, happens to be analytic in almost the entire complex z plane. However, the presence of this 1 by square root of 1 minus z square factor tells you that z equal to 1 and minus 1 are difficult points. In fact, they are singular points because of the 1 by 1 minus z square in the exponential. Also, what you have to do in order to make the function single value is to put in branch cuts from minus 1 to minus infinity along the real line and from plus 1 to plus infinity. The presence of this branch cut is very important in deciding exactly how changing this omega t over large intervals would actually affect this particular value. In fact, that's exactly the origin of the Maslov factor. But remember, what we are doing is we are keeping omega tau confined to within 0 to pi, and then e to the minus I omega tau will stay confined to the lower half plane, will not cross the branch cuts. That actually is the reason for breaking up omega capital T into capital N pi plus omega tau. Now, with this in effect, the propagator simply becomes, apart from the factor square root of m omega by pi h cross e to the minus I pi by 2 capital N, e to the minus I omega tau by 2 and e to the minus zeta a square plus zeta b square by 2, you have the Mehler function. I have a spelling error here, it should be Mehler, with arguments zeta a minus 1 to the capital N times zeta b, and z, of course, is e to the minus I omega tau. Now let us focus on these tau dependent pieces here, as well as zeta a zeta b dependent pieces. If you look at this is square root of e to the minus I omega tau. I am just writing that as square root of z, curly g, zeta 1, zeta 2, semicolon z, e to the minus zeta 1 square plus zeta 2 square by 2. Here, of course, zeta 1 and zeta 2 are going to be zeta A and minus 1 to the capital N zeta B. Of course, squaring that will still give you zeta 2 square. This is, of course, the same expression as the one we had a while ago, except for the fact that you have an extra factor of root z. But now we have to be a bit careful that if z is e to the minus I omega tau, then what trigonometrical expression does this reduce to? Now you can easily see that you have an overall square root of z by 1 minus z square, and you also have a z by 1 minus z square multiplying twice zeta 1 zeta 2. It's very easy to see that z by 1 minus z square turns out to be 1 over twice I sine omega tau. If you look at the ratio of the two terms in the numerator of the exponent, you will see that what you have is 1 plus z square by 2z. That is, if you take z common out from the whole expression, you have a z by 1 minus z square multiplying the whole thing. Then you have twice zeta 1 zeta 2 minus half 1 plus z square by z into zeta 1 square plus zeta 2 square. And 1 plus z square by 2z is actually very simple. It's cos omega tau. Using these, we can put this back in our expression for the propagator, and you end up with an exact expression for a propagator which works for all capital T. Square root of m omega by pi h cross, it is a minus I pi by 2 capital N divided by square root of twice I sine omega tau, exponent of I by 2 sine omega tau, that's actually minus z by 1 minus z square, so I'm changing the sign inside as well. Zeta a square plus zeta b square cos omega tau minus 1 to the n zeta a zeta b. So this looks very similar to the expression that we had earlier for the propagator, except that instead of capital T, we now have tau, and also we have this extra factor of e to the minus I pi by 2 capital N, which we had already argued about previously, the Maslov factor. But there seems to be another extra minus 1 to the n stuck within the exponent, multiplying zeta a zeta b. But now let us try to relate all these back to capital T. Now since omega tau is omega capital T minus n pi, it follows from elementary trigonometry that sine omega tau and cos omega tau are basically minus 1 to the capital N multiplying sine omega t and cos omega t respectively. Sine omega tau must be positive, omega tau being in the first two quadrants, so sine omega tau can also be written down as mod of sine omega t. And using this, plugging this back in the propagator formula, what we get is we have this extra factor of e to the minus I pi by 2 capital N, then your square root of m omega by pi h cross times twice I sine omega tau, but that's magnitude of sine omega t. This is exactly the normalizing factor that we had found out a while ago, using the argument based on the Euler product. And then we have an exponent where the minus 1 to the n simply cancels out between the numerator and the denominator. The cos omega t, sine omega t, and the final term all have minus 1 to the n's, and they cancel out. So you are back to exponential of I by h cross times s classical. And so we have in a sense come full circle. As I said before, we have derived the energy eigenvalue and eigenfunction from the propagator, at least from the propagator that we had for capital T between 0 and pi by omega. And now we have used exactly those expressions and the spectral representation to extend the propagator beyond that particular time interval. And figured out that apart from the fact that sine omega t within the square root is replaced by a mod of sine omega t, you have an extra factor of e to the minus I pi by 2 for every time you cross a multiple of pi as far as omega t is concerned. The only question left is what happens when omega t is exactly equal to a multiple of pi. Let me quickly turn to that next. The answer actually is very, very simple to work out if we start from the spectral representation. Indeed, we don't even need the exact forms for the wave functions for this. All we need are the energy eigenvalues and the fact that the wave functions have specific properties. So, in the expansion, what we have done is we have put in omega capital T equals capital N times pi. And since e to the minus I pi is minus 1, this actually becomes a sum from n equal to 0 to infinity of minus 1 raised to the power capital N times small n, psi n xb, psi n star xa. Of course, you have a factor which is independent of small n, which has been pulled outside the sum. This, of course, is nothing other than the Maslov factor that we have been meeting over the last few minutes. Now realize that minus 1 to the power capital N can be absorbed within a wave function simply by using the fact that psi n is either an even function or an odd function of x, depending on whether small n is even or odd. And using that, you can rewrite the sum in this form. And just to make the thing clearer from this point on, we replace the wave functions by the overlaps with position eigenkets, and you end up with e to the minus I n pi by 2 sum over n going from 0 to infinity of xbn, the overlap, times n overlap with minus 1 to the n times xa. Given the fact that the sum over n of the ket n bra n combination is nothing but the identity, this simply becomes an overlap between position eigenvectors with eigenvalues xb and minus 1 to the power n times xa respectively. And so you end up with e to the minus I n pi by 2 times the delta function of xb minus 1 to the n xa. So as you can see, the propagator really becomes singular when omega t equals an integer multiple of pi. In fact, it becomes singular like a delta function, and it vanishes unless xb is equal to xa if capital N is even, or xb equal to minus xa if capital N is odd. The reason behind this singular behavior of the propagator can be traced back to classical mechanics. Remember, we are looking at paths which join xata to xbtb, and typically we will have only one classical path which obeys these boundary conditions. Of course, when we are calculating the path integral, we are taking contributions from all paths, but you must realize that the classical paths do tend to dominate in a sense that since for classical paths, the contributions from neighboring paths are almost identical, there are no cancellations. This is of course the reason why in the classical limit, the propagator implies the principle of least action. Now, let us just examine the scenario with respect to classical paths here. If you start with any arbitrary point xata here and start with any arbitrary classical path, here the slope of the classical path of course indicates the speed at that point. Almost certainly this path will miss xbtb. There will only be one unique initial condition typically for which the path will go and hit xbtb. We are of course talking of classical paths only here. And we have already seen how to figure this out. After all, to figure out the precise classical path, we use the initial conditions that are t equal to ta, x is equal to xa. So you must have this relationship. And for the path to pass through xb at time tb, you must have xb is a cos omega tb plus b sine omega tb. Now these are two simultaneous equations for the two unknowns a and b. And in the typical scenario, you would be able to solve for them, plug them back here, and that will give you the unique classical path which joins the two endpoints. However, if we are in a situation where omega tb exceeds omega ta by n times pi, then trigonometry tells us that cosine omega tb and sine omega tb are both minus 1 to the capital N times cosine omega ta and sine omega ta respectively. And that will show that under such a situation, these two equations are no longer independent and typically will not have a solution, except if the following condition is met. So, what we end up with are no classical paths at all for arbitrary values of xb when tb and ta differ by integer multiples of half period, or if xb happens to satisfy minus 1 to the n xa, then any path which goes through xa ta will also go through xb tb. Any classical path, that is. So, on the one hand, you may not have any classical paths at all joining the 2 points if xb is not equal to minus 1 to the n xa, or if xb is equal to minus 1 to the n xa, you have infinitely many classical paths. Now, since each classical path contributes a finite amount to the path integral, the presence of infinitely many classical paths indicate that the path integral will diverge, as it does. This is the reason why the path integral vanishes whenever xb equal to minus 1 to the n xa is not satisfied, but does not vanish and diverges when xb equal to minus 1 to the n xa is satisfied. Of course, all this is in the context of tb minus ta being an integer multiple of pi by omega. Now, while on the context of classical mechanics, let me point out something which we actually met before in this lecture, but I did not bother to point it out then, basically because we were not really looking at classical mechanics aspects then. We were focusing on the path integral. Remember our expression for the action S for an arbitrary path x happens to be equal to the classical path plus this m by 2 integral from ta to tb of x dot square minus omega square x square. And by using the Fourier decomposition of the paths, we managed to rewrite this extra term in this form: mt by 4 plus an infinite sum, where the infinite sum has pi square k square by t square minus omega square as coefficients of bk square. Note that when t is less than pi by omega, then for each and every one of the terms in this infinite sum, the coefficient happens to be positive. And that tells you that no matter how you vary your path, remember we are only varying paths with the endpoints fixed, which is where we got this Fourier decomposition from. For all such variations, the additional term that you get, the term over and above S classical, has to be positive. So we recover a very well-known result from classical mechanics, that the classical path is a path of least action. And now let me point out that classical mechanics does not really say that the classical path has to be a path of least action. What it does say is that the classical path is a path of stationary action. Least action fits in so nicely with the concept of a lazy god or some such story that it has become very, very popular. But let me now point out that the moment the time interval capital T exceeds pi by omega, then some of the coefficients of this additional term become negative. For example, if capital T is between pi by omega and 2 pi by omega, then the coefficient of b1 square is negative. All the other coefficients are positive. But this now indicates that there will be some paths for which the action will actually go down from the classical path. In other words, the classical path is no longer the path of least action. It's still the path of stationary action. All the variation is to quadratic order in the BKs. So, to first order there is no variation. But quadratic variations could even bring the action down. You get more and more negative coefficients if capital T exceeds more and more multiples of pi by omega. In other words, The classical path for the harmonic oscillator actually is a saddle point for the action unless the time interval between the 2 points of the path is less than half a time period. It's only for time intervals less than half a time period that you truly have least action. Otherwise, the action is stationary, but it can go down or up depending on what kind of fluctuations you're talking about. In today's lecture, we have seen one more way of evaluating the propagator for the harmonic oscillator. And you might think that we are done with this particular system. However, this particular system will still occupy us over more lectures. Firstly, we are going to take a look at a generalization of this particular harmonic oscillator to a more general quadratic potential, perhaps even a time-dependent potential, which we are going to talk about next time. We are also going to talk about coherent state path integrals in a later lecture. And for harmonic oscillators, as I have already promised, will also be there. And that means that we are stuck with the harmonic oscillator for quite some time in the future. Anyway, let me sign out today. We are going to come back with more of harmonic oscillator and their path integral quantization in later videos.